More than two colors. We have seen in Theorem 11.6 that a bipartite graph cannot have too many edges. We have also seen that if we want the bipartite graph on m vertices that has the largest number of edges, we have to take the bipartite graph in which the numbers of vertices in the two color classes are equal, if n is even, or differ by 1 if n is odd. Let us generalize this question into k-colorable graphs instead of bipartite two-colorable graphs. Is it still true that the best strategy to maximize the number of edges is to split the vertices among the color classes as equally as possible? The following famous theorem of Paul-Turan shows that this is indeed the case. To prepare the statement and the proof of Turan's theorem, let n equals to tk plus r, with r which is less than equals to k minus 1 but greater than equals to 0, and divide the n vertices into k subsets. All of them are size t plus 1, and the rest of size t. In other words, we divided the n vertices into k blocks, and whose size are as equal as possible. Let two vertices be joined by an edge if and only if they are in different subsets. The graph H obtained is a complete k-partite graph. The number of its edges, see exercise 1, is t of nk is equals to k minus 1 divided by 2k times n squared minus r times k minus r divided by 2k. It goes without saying that H is k-colorable, as we can assign color 1 to the vertices of the first subset, color 2 to the vertices of the second subset, and so on. Now we are going to show that no k-colorable simple graph on m vertices can have more edges than H. Theorem 11.15. Let G be a simple graph on m vertices that contains more than t of nk edges. Then G contains a k plus 1 subgraph. In particular, G is not k-colorable. Prove let G have m vertices, and let G contain no k plus 1, and let it have the maximum number of edges possible. With these conditions, we will prove that G can contain at most t of nk edges. We will proceed by induction on T, where T has been defined in the paragraph preceding the theorem. If T is equals to 0, then the statement is obvious. Now assume we know that the statement is true for T minus 1. Our conditions imply that adding any H to G would create a k plus 1 subgraph. Therefore, G must contain a k subgraph, say S. Now we will count how many edges G can have. The edges of G can be within S, or between a vertex of S and a vertex of G minus S, or within G minus S. There are k choose 2 edges within S. Each of the vertices of G minus S can be connected to at most k minus 1 of the vertices of S. Finally, G minus S has n minus k, which is equals to t minus 1 times k plus r vertices. So, induction hypothesis implies that there are at most t of n minus k edges within G minus S. Therefore, the number of edges in G is at most k choose 2 plus n minus k times k minus 1 plus t of n minus k, which is equals to t of nk. This shows that if G has more than t of nk edges, it must contain a k plus 1, and therefore it cannot be k-colorable. We admit that we swapped two technicalities under the rug here. One was the computation of the number t of nk of edges in our complete k-partite graph H. The other is the proof of equality. 11.2. That is k choose 2 plus n minus k times k minus 1 plus t of n minus k is equals to t of nk. See exercises 1 and 2 for these details. Theorem 11.15 proved in a rather strong way that certain graphs are not k-colorable. Indeed, it proved that graphs containing too many h's will always contain a k+1 subgraph, and therefore are not k-colorable. We certainly know that a graph does not have to contain k+1 in order to have chromatic number, at least k+1. Indeed, if G is an odd cycle of length more than 3, then it does not contain K3 and still has chromatic number 3. What is interesting is that in some sense, odd cycles and complete graphs are alone in forcing high chromatic numbers. This is the content of the following theorem of Brooks that we state without proof. Theorem 11.16, let G be a graph which is not an odd cycle and not a complete graph, and let D, which is greater than or equals to 3, be a positive integer, so that each vertex of G has degree at most D, then the chromatic number of G is less than or equals to D. On the other hand, note that for all n, there exists a graph that contains no triangles, but has chromatic number n. This is the content of exercise 6.